Hi, thanks for tuning into my talk. My name's Thomas Munro. I'm a Postgres developer, and I'm going to be talking a bit about the history and potential future of SLRUs in Postgres after a bit of an introduction to explain what these strange things are. So the structure of the talk is I'll give a super short overview of what I'm trying to achieve. Then I'll look at a bit of history, and then move on to talking about my development prototype. So the super short version is that SLRUs are special caches and disk storage systems for storing 7 specific types of transaction-related data. And I'll explain in more details what I mean by that in a moment. I'd like to keep the file management part of the SLRU system unchanged, at least in this project, although obviously there are some things that could be improved. But I think it's interesting to explore the idea of replacing the cache that's used for each of these SLRU sort of data containers, and replacing that and putting that data into the main buffer pool. And this talk is pretty much contrasting those different approaches and why I think it would be a good idea to consider unifying the buffer pools. And this is about exploratory work. It's not a finished product. It's it's far from complete, and there's plenty of pieces of this work that could be debated. So at the moment, if you look in the PGCon allocations view, you can find, among other things, these 8 different buffers are listed, and these are pieces of shared memory. The bottom one that you see here on the screen, buffer blocks. I'm actually running Postgres here with shared buffers equals 1 gigabyte, and you can see that 1 gigabyte of space there. The total amount of shared memory used by Postgres is much more than 1 gigabyte, because there's many of these other special buffers and some other control objects and wall buffers and so forth. So there's all kinds of other things in shared memory beyond the 1 gigabyte that you tell it to use for shared buffers. Shared buffers is kind of synonymous with the main buffer pool. The other 7 lines you see there are much smaller amounts of memory. The biggest ones there are 2 megabytes for transaction exact and commit TS. And you can see on the right I've shown how there's a bunch of files on disk, and the main relation data that currently is the only thing that goes into the main buffer pool is stuff under base. It's got relation files, index files, table files, that kind of stuff. But the SLRUs, the other 7 things here, it's these files that have hex numbers: PG subtrans, PG exact, and there's 5 others. The concept I'm exploring here is getting rid of those 7 special SLRU caches and just putting that data into the main buffer pool. So the files would be exactly the same on disk. It's just that the data that lives in those caches would have to compete with relation data using the normal rules of the buffer replacement policy, so that hopefully the most valuable data would be there. And instead of having small fixed size buffers or buffer pools, if some data is worth caching to avoid I/O stalls, then we'd cache it. If it's more valuable than some index that you never look at, you can use some memory. It's competing with everything else in the system, and that's kind of the goal of a buffer pool. But the size of these SLRU buffer caches is a very obvious problem with the design. At least it's obvious once you get into a workload that needs more cache to be effective and can't have it because our memory is arbitrarily chopped into these partitions. But there's also some more hidden problems, which come from the fact that the buffer pool is a much more sophisticated design than the mini SLRU buffer pools. The main buffer pool is also a point of integration for all kinds of future development plans involving encryption, asynchronous I/O, even existing things like checksums for all the data in the database don't work in the SLRU buffers right now. And that's because it's a separate implementation. So it's not just the size that I'm worried about. It's also integration with current and future plans for Postgres development. So the three questions that I'd like to get to the bottom of are, can we unify all of these SLRU caches with the main buffer pool without slowing anything down? And beyond that, can we speed anything up? Well, I know we can. It must be true that we can speed things up in cases where we finish up using more, having more space. But maybe there's even an opportunity to speed things up with the existing amount of space. I don't know the answer to that question. And finally, maybe the most important question, should we future-proof all of this core transactional data by putting it into the main infrastructure, which is kind of where many future features sort of meet. Okay, so now I'm going to give a super brief overview of how we got to where we are with these SLRUs. Where did they come from? What are they? So back in the days of university Postgres in the late 80s and early 90s, there was no traditional transaction log. There was something called the transaction log, but it wasn't what we call a transaction log today. There was no wall, is what I'm trying to say. Instead of that, there was this minimalist log that just recorded which transactions committed and which aborted with 2 bits per transaction, and we still have that. That's called the C log today. And there's a long history, and many people have commented and written about how Dr. Stonebreaker, who worked on the Postgres project at Berkeley, did not like the Aries recovery algorithm or systems like that have a wall and a complex set of rules for recovery, and experimented with a completely different approach. Most other systems don't have, as far as I know, something like our C log, because they have other ways of making sure that nobody sees uncommitted data. Either they lock everything and roll back when they need to, so that other people have to wait while data is in an uncommitted state, or they have some kind of snapshot system, which is to an end user much like Postgres, but implemented completely differently using undo logs. So they don't have a thing that is similar to our what they called the transaction log, and the code that lives under transam in the Postgres source tree, transaction access method. So back before Postgres 7.2 came along, that data that lives that lived in the transaction log, it was actually in the main buffer pool because it existed in a special kind of pseudo relation, like a table called PGLog. And there were a couple of problems with that. One of them was that it kept growing bigger and bigger and bigger. There was no way to throw away old data, so that there was a file getting bigger on disk. And back in those days, disk was much more expensive and space was an issue. So, and the secondary problem was that when the transaction ID was 32 bits, and it could only grow up to the maximum value of a 32-bit integer, and then the time essentially ended. The only way to continue working with your database was to dump it and reload it. So in 7.2, the famous transaction wraparound was invented so that you didn't have that end of time problem. And also the PG log, as it was originally known, was chopped, instead of being in a regular relation file and in the main buffer pool, was chopped into smaller files. They're 256K. I guess that was probably the way they were chopped originally back in 7.2. I haven't checked. So that you had a series of files called 000, 001, 0002, and you can, if you need to, once you can prove that you don't need data older than a certain point, which I'm not going to discuss that logic in this talk, but somehow you can, there's a sliding window of data that you actually need, and having it in these chunks enables you to get rid of the old files. So that was kind of the goal, but at the same time as implementing that, it was also, the caching was also kicked out of the main buffer pool. I don't know, I couldn't find a discussion of why exactly that was done. It was possibly the implementation was easier for these other concerns that were very important. At that time, it was also renamed from PGLog to PGClog in various places. Now we know that particular directory as PGExact or exact in some places, or CLog in other places. So there's kind of multiple names floating around for this thing, which I mostly refer to as the CLog. So after that was done, many other uses were found for the same idea. The CLog was originally, in 7.2, was some code that just dealt with transaction IDs, storing them in this special side buffer pool. But then the mechanism was generalized to support subtransactions. That's the save point mechanism. Multi-exacts were added in 8.1 that allowed shared locks, because we needed a place to store. I wasn't involved in that work, but Postgres needed a place to store lists of the transactions that are that all hold shared locks on a tuple, for example. And later, other uses were found as well. They all notify, I guess, is a bit different because it's arbitrary data that's stored in a buffer. Serializable is more like the others in the sense that it's related to transactions, so it sort of makes sense that it's something under the transam directory and reuses that machinery. So I'm going to go quickly through some ways that I think the main buffer pool is better than the SLRU code. In terms of lookup, the SLRUs were originally designed to be small. And so they use a simple linear search for buffers, which makes a very large amount of sense for small buffers because scanning a very small array looking for an integer is super quick. The locking is very simple. There's just one lock essentially for each SLRU, although there's something special for I/O, which I'm not going to talk about. But instead of so that works pretty nicely when SLRUs are very small. If it makes sense to have very big SLRUs, then that design begins to break down. The main buffer pool, on the other hand, has a separate buffer mapping table, which is a partitioned hash table. So many people can be doing it's a hash table, so it can be really, really big. I mean, potentially you might have many gigabytes or hundreds of gigabytes or even more in the future. And people can be looking things up in the buffer mapping table concurrently, just not in the same partition concurrently. And then in terms of locking, rather than just having one big lock for everything, there's a whole bunch of different mechanisms. There's buffer pins, there's a system for atomic flags that are in the header of a buffer descriptor, and then there's content locks. So one question is, which of these things do we actually need to do the work we need for SLRUs? And I'll talk about that in a minute. Another point of comparison between SLRUs and the main buffer pool is the buffer replacement algorithm. So buffer pools obviously have the difficult job of deciding which data you need most in the future. They can't see into the future, so they have to make predictions based on past performance, which is notoriously difficult. The SLRUs use an approximation of least recently used, which is, essentially, which is obviously where the name comes from. Simple least recently used cache is the naming origin for that. The replacement algorithm that it uses performs a linear scan to find the least recently used buffer. So at some scale that won't work anymore. If we're dealing in tens, hundreds of buffers, maybe it's fine, but once we get to serious numbers, it falls down. The algorithm used by the main buffer pool isn't state-of-the-art, admittedly. It is a generalization of the clock algorithm, which is very widely used it originally came from Multics, the operating system that preceded Unix, but has been modernized in a few ways over time. There are some cases where it doesn't perform too well, and it's entirely plausible that it will be improved in the future. I don't really see that as an argument not to use the main buffer pool for something. I see that more of an argument for, continuing to look into ways to improve the main buffer pool and making sure that all of the data that we're trying to cache will benefit from future improvements. But in any case, it's certainly better than what SLRUs are using for buffer replacement, at least at scale. And I'm not really trying to criticize the way it was done, because it did make sense for smaller caches at the time. And it's faster for smaller caches in some cases, which I'll talk about in a moment. Another thing is that the SLRU system doesn't have anything helping it. There's no extra infrastructure to help it write back dirty data, other than checkpoints, which happen in the background, but they're infrequent. Whereas the main buffer pool has a background writer process that tries to make sure that clean buffers are always available, and it also does some write back concurrency stuff, at least on Linux it does. And again, the background writer may not be ideal, and there are plenty. I'm aware of work to improve the way that system works, but yet again, the general sort of idea I'm trying to present here is that by using the standard infrastructure, you can benefit from not only what we have today, but also future improvements in that area. So it means that when you decide that you need to load a page in to the some like a C-log page in or something like that, it's much more likely that you'll find a page to replace without having to write dirty data out, which means that you won't have to make a write system call, which would be bad, and that's a good thing to avoid. Now, before 13, in fact, the write back for SLRUs was much, much worse from a synchronous system call point of view, because we used to call fsync when writing out, when evicting a page from one of the SLRU caches. In fact, that was kind of one of the first pieces in this series of work. Something that I collaborated with Sean Debnath on, who's someone who's interested in this whole area as well, unifying buffer pools. And so that was kind of a first step to making the data from SLRUs behave more like regular relation data, getting the checkpoint mechanism to take care of f-syncing your data instead of doing it synchronously when you're trying to, just because you're trying to load an SLRU page in. So, yeah. Another thing which I mentioned earlier is checksums. Now, my prototype code that I'm talking about today doesn't actually do this right now, so this is something that becomes possible with a unified buffer pool. So at the moment, pages in the main relation data files optionally have checksums, and those are computed whenever we're writing data out, and when data is read back in, we can verify that and find out if maybe the file system is lying to us, or there are bugs somewhere, or some files have somehow been messed up. Nothing like that happens for the SLRU data, even though it's quite critical data for interpreting the state of the whole system. Whether individual transactions committed or not is kind of a big deal. So that's something that happens. It's kind of built into the buffer pool, or coordinated by the buffer pool and other parts of the system. And the SLRUs don't have that. So that was something that exists today that doesn't work in SLRUs and could work if we unified. But there are also future improvements and external projects doing really interesting stuff with the buffer pool that SLRU data doesn't currently benefit from and couldn't benefit from unless we did a bunch of work or unified. One example is the Neon project, which I believe there's a talk about at PGCon 2022. So that's a distributed wall-aware block storage system that's integrating with Postgres at the buffer pool level. I don't know too much about Neon, but I assume that it's going to be very helpful to any project working along those lines if the main transaction data is treated normally, the same way as other data, other buffered wall-logged stuff. Another project which I am involved with is the AIO proposal for Postgres, which adds a bunch of support for using OS-specific asynchronous I/O facilities or background jobs, background processes to do a whole bunch of new kinds of I/O tricks, including scatter-gather and merging I/Os and so forth. That's integrated with the buffer pool because the primary goal of that thing was to get well, also wall data, but it was to get the large chunks of main relation data to be processed in that way, scatter gather and so forth. That could apply for free to the SLRU data simply by getting on that bandwagon and using that sort of central infrastructure for buffered data. Another one which I think is probably pretty interesting to a lot of people is transparent data encryption, TDE. There's a number of different groups working on adding TDE to Postgres, and that's, I assume, going to be pretty similar to the way checksums integrate. I don't know too much about those projects, but I do know that they are tightly integrated with the main buffer pool. And as I mentioned earlier, perhaps one day we'll have a better buffer replacement policy implemented in the main buffer pool, something more modern that's scan resistant, something like CAR or something like that could come along. And it would be nice if, again, all of the core transactional data benefited for free from those new facilities. So how would this reunification actually work? I say reunification because, as I mentioned earlier, the C-log data was originally in the main buffer pool, as incidentally was the commit timestamp data. So that's two of our SLRUs that used to be in the main buffer pool. So the first question I wondered about is how should the buffer tags look? At the moment, pages of data that are in the main buffer pool have a buffer tag to identify them. It's made of 5 32-bit words. It would be nice if that was 4 32-bit words, but I'm not trying to rearrange anything here. I'm just trying to fit into the existing scheme. And what I've come up with is borrowing an idea from the zheap project, is putting a special database OID in there, a database OID that will never be allocated for a database, and then the rel file node can store the SLRU number, and the block number is used for the block within the SLRU, and everything else is given a default value. Other schemes will be possible for this. People have suggested using some of the fork number bits or some magic tablespace values. I'm not super attached to any of these particular ideas, just something that works and is easy to dispatch on. I'll talk about that in a moment. The next question is, how should the buffer pool deal with raw pages? So for now, I don't want to change the file format or the page layout for SLRU pages. Ultimately, we would want to do that, I think, if we wanted to get checksums to work. And then you'd need to make it so that PG Upgrade could rewrite those files and do the right kinds of stuff. For now, I just want to avoid the problem of checksums and LSNs, which are another part of the standard page header, because I don't want to change the file format. So that means that I need to have a place to store LSNs associated with each page. Relation data has the LSNs in the actual page data. For the SLRUs, it's stored in a separate array. And so I need to, if I throw away the SLRU cache machinery, then I need to invent a new place to store LSNs associated with each page when we can tell that it's a raw page. So basically you need some way to say, this is a raw page. And at the moment, that's a macro that checks for the special database OID, which is a bit weird, bit of a rough edge. In the long term, I would like to see that data made normal with checksums and LSNs, so that normal tools and normal code doesn't need any special handling. The next thing I wondered about is how the storage manager should... So when the buffer manager wants to read or write data to or from disk, it asks the storage manager. So the buffer manager needs to know about raw pages only, but it doesn't really know anything about how and where the data goes. On disk, it tells the storage manager to read and write for it. Now, historically, luckily, the storage manager code in smanager.c had a place to dispatch to different implementations. At the moment, there's only one implementation that handles regular files on disk, but that is an integration point for new kinds of storage. I don't know if it's the best integration point. It certainly works pretty nicely, So I added support in my prototype for SManager to figure out how to deal with these special database OID data files. So it knows how to find its way to the existing file layout of SLRUs. So for example, PG_exact has segment files 0000 and so on, as you can see on the slide. The next thing I worried about is whether the existing very simple locking scheme would, just through its simplicity, always be able to beat whatever we do with the main buffer pool. The main buffer pool has, it doesn't just have a single lock, find the page, modify the page, and then unlock. Instead, it has two steps. You've got to find the page through the buffer mapping table, and then you've got to do something, some level of locking with the buffer page, at the very least pinning it. So my current theory is that in many interesting common cases, we don't actually need locking any heavier than simply pinning the page. Pinning is just a way to tell the buffer pool not to kick this page out of the buffer pool, just to keep it stable where it is. But then I think it's possible, for reads at least, to read, for example, the C log without having to take a heavier lock than that. For writing to a C log page, a naive idea would be that you would take the content lock exclusively, so that you don't finish up corrupting a byte that someone else is writing to. But I think there are some better ideas than that I'll get to in a moment. As for trying to avoid the extra cost of the buffer mapping table lookup, I found that it's pretty easy to avoid that in common cases by having a small cache of buffer numbers, like page numbers to buffer numbers, and trying to use that, because actually a lot of these pages get accessed many, many, many times, especially the C log pages. They're super hot in some workloads. They get very high numbers of cache hits on a single page repeatedly. And it's almost certainly, the page is almost certainly going to be in the same buffer each time. So using the read recent buffer interface, you can make it so if you think you know which buffer a page is in, but you're not sure, you can try to open it with, you can try to get your hands on it, try to pin it with read recent buffer. And if it, in the unlikely case that it's moved, it'll just say no, sorry, and you'll have to go through the slower lookup path. And in this way, you can actually avoid having any kind of, expensive sort of blocking or anything like that to do a lookup and find your way to the buffer. Which means that, in theory, you might hope that pinning and then accessing and then unpinning a page might be about as good as the existing SLRU system, which acquires an LW lock, does its linear search for a page, modifies the data, and then releases the LW lock. And I'll tell you about my experiments with that in a moment. Another problem that comes up is how to throw data away. SLRUs, the kind of reason that the SLRU mechanism was invented was to be able to throw data away on disk. So because it's kind of it's more like a queue in some ways than a relation. And the problem, if you've got a bunch of data that you want to get rid of, it's going to be a page range. It's going to be, pages n through m of a given SLRU. You need to find all those pages and kick them out of the buffer pool. But if that's mixed in with gigabytes of other data, you certainly don't want to go scanning through the whole buffer pool looking for it, because that would really suck performance-wise. That's what the existing SLRU system does, because it's in these tiny SLRU special caches. So instead, in order to discard ranges of SLRU data, we need to loop over the page range, looking up those pages and discarding them if they're found, which doesn't sound that great. Fortunately, I think in most common cases that stuff's going to be happening in the background. So vacuum deciding it can advance the oldest XID in the system and throw out some C-log, or checkpoints deciding that it's time to trim the subtransaction data. So, that kind of stuff shouldn't be in the way of any user transactions, I think. I haven't got to the bottom of that fully yet, but I think probably that type of discarding is probably going to be okay. And I think probably, and recently in recent Postgres releases, work was done to make dropping tables a little more like that in some cases. Because when we dropped tables, we used to always, we have to do a full scan of the buffer pool, looking for anything from that table to kick it out, because we don't have something like a tree-based data structure for the mapping table, so we can't actually scan in order for a given relation. And that's recently we've done a little bit of work to make it so that in some cases we can probe a range of blocks rather than when dropping tables. So the same sort of thing applies here, except that in the SLRU case, hopefully in most interesting cases, it's not something that a user is waiting for. Another thing that I ran into, and I think this is more of an opportunity, I hope. I don't have code for this right now. I have ideas, but there is a grouped clog update mechanism. When you commit a transaction, we write to the log, the wall that is, and then we update the C log to say that transaction committed. But there's a mechanism for doing grouped updates. If you've got huge numbers of sessions running concurrently, all trying to commit loads and loads of transactions that are most likely on the same page if they're short transactions in a PG bench type or type workload or OLTP of any kind, with very short-lived transactions. The transactions that are committing concurrently are almost certainly going to be on the same C-log page. So we have this group C-log update scheme, which if it sees someone else is currently locking and updating the C-log page, it will put some information on a list, which allows one locker to apply the C-log updates for other backends, which sounds good, but if you're going to sleep while waiting for that to happen, it's still kind of bad. And while I was thinking about what type of locking you actually need to access C-log pages, initially I realized, you probably only need a pin to be able to read it. If we had this is an idea, and as I say, I don't know if it's a good one. I think it must be better than going to sleep if you can keep all of the concurrently committing backends on CPU and have them use atomics to update the C-log page. Now, updating buffer pool pages with atomics and not using any other kind of locking other than just a pin to make sure the page doesn't move underneath you would be somewhat new. And whether that's something we can make work, I don't know. But in my prototype for this system, I needed a way to get rid of the extra infrastructure that's kind of hanging on the C-log system. And that's when it occurred to me that maybe what it's doing right now is not even that great. And perhaps we can, as a sort of a side project, actually get rid of that infrastructure and come up with something that actually works faster. But, instead of making bold claims without proof, I should probably go and hack on that. That's just an idea I wanted to mention. Okay, so that is all the ideas that I wanted to talk about, and now it's time to talk about my prototype code. So I've created a commit fest entry, and there's a mailing list, which is mailing list thread, which is so far very short. So commit fest entry is 3514. From there, you can find the thread where I've posted early experimental patches. I'll post a rebase with an updated version before this goes out. there are tons and tons of open questions, and especially around the locking stuff that I want to look into some more and get other people's ideas about if I can. But excuse me, the patch runs well enough to explore some basic ideas and sort of see the thing working. It's certainly got all kinds of bugs and things that aren't yet resolved. With a patch applied, you can use the PG buffer cache extension to inspect the contents of the usual main buffer pool, and you can see stuff in Magic Database 9. Here I've written a query to translate the rel names into the directory names of the different SLRUs so you can know what they correspond to. And you can see here I've managed to get 3.5 megabytes of CLog into my buffer pool, and that's after running about 10 minutes of PG bench on an 8 megabyte system. And that's obviously more than would fit in the standard 1 megabyte buffer. Earlier I showed on a slide that there was 2 megabytes of memory occupied by the exact SLRU, aka the CLog. I didn't go into how there's 1 megabyte of actual CLog data and 1 megabyte of LSNs. That's a topic I didn't quite have time to get to, but I'll discuss on the mailing list. And so this is 3.5 times more CLog data, which means that we're avoiding potentially a huge number of misses that lead to system calls. As for whether the cost of making lookups is higher, currently it is, and I'm working on that. So here you can see a very simple test I made that goes and looks up a whole bunch of XID statuses in the CLog, and they're all cached. So this is pure, how long does it take to look up 8 million XID statuses? And you can see that the second time there is, something like 50% slower. And that's something that I need to get to the bottom of. Basically, here we're looking up pages and using read recent buffer. So we're pinning, reading the bits we want, and then unpinning, and that turns out to be slower. I haven't quite explained to myself why that is, why that should be slower than acquiring the SLRU LW lock, which is a share lock, but the CAS for the pin should be hopefully kind of similar. Apparently it isn't, and I need to look some more into that. But while studying that, I started to wonder whether, if you look at the number of CLog hits that we do, it's so high. Like we really hammer the CLog during an OLTP workload like PGBench. Of course, PGBench is kind of a torture test for any cache. It's as soon as the working set is bigger than memory, it's uncacheable because it's random. So, it's kind of a worst case for any caching system. But still, in this case, it's all in memory, and the hit rate is very, very high. It really made me start to wonder if we should be using something completely different to look up CLog commit statuses. I did build an experimental cache that sits in front of all this and just has a megabyte of memory with 1 bit representing every 256 XIDs. And if it's on, then every transaction in that 256 XID range committed. Which probably immediately you'll say, but what about my workload where every 10th transaction aborts? And it's true that won't help with that. But if you, I don't know, it sort of feels like there must be some way we can do something that is some way to compress this information into a piece of memory that we can access with atomics, so that we don't need to go through all of this extra work to do these highly frequent accesses. I don't know how to do that. That's kind of a side experiment that I did when I was wondering if maybe even trying to make this thing as fast as the existing SLRU for smaller SLRUs is even worthwhile, or maybe it's trying to solve the wrong problem. And I haven't really got an answer for that. But these are some of the things that I have been working on. In fact, originally when I proposed this talk, I was expecting to travel to, this was just before things got worse and then the conference went online, and I was sort of, my reason for bringing this early stage work to PGCon is really that I wanted to discuss it with people and see. I know that other people have probably got ideas and could help me figure this stuff out in the in maybe in a conference session or in hallway track discussions. I'm going to try to make the Q&A on IRC, and I hope to see you there, and maybe we can talk about some of these problems and how they could be solved. Thank you very much for listening to my work in progress talk. Sorry I don't have a complete whiz-bang finished product here, but it's I think it's an interesting area to explore. Thank you very much, and maybe talk to you soon.